I'm with Davide Scaramuzza from the University of Zurich. Davide, you've just presented about human-level performance with autonomous drones. Could you just outline the principle of your presentation?
So the presentation delved into how we can use standard cameras or bioinspired cameras in order to improve the agility of flying robots, and how the results and the findings of this research can be transferred to other platforms to make robots more robust and safe than they are today.
Okay, I picked out a few themes that seemed particularly pertinent. For example, you talked about the limits of a perception, planning, and control model, and that this was prone to imperfect perception and the effect of unmodeled effects. Would you like to elaborate on that?
Yeah, so robotics has been very successful. Today we have more than 40 million vacuum cleaning robots that are cleaning our houses, and we have also the beginning of autonomous cars and other applications. And this has all been thanks to a very simple control architecture called perception, planning, and control. This architecture is very good when driving robots up to certain speeds, but actually starts to fail when you increase the speed and the agility of the platform, which is the case, for example, for robots that you want to become more productive than humans, because if you want to be productive, you have to be a bit faster than humans. And the reason why the standard perception, planning, and control architecture fails is because it's fragile to imperfect perception and unmodeled effects. I'm thinking of lack of data in the camera images, motion blur, pixels being saturated when the sun shines in the field of view of the camera, or for example, the vortices, the turbulences that the drone encounters when flying fast. All these effects are very difficult to capture with the standard models, and that's where machine learning has proven useful.
Okay, thank you. All right, you gave an example of a test scenario involving a human pilot. I think the name was Marvin, who was the Swiss champion, age 15. What contribution did that make to your research?
Yes, so some years ago, I got funding from the European Research Council to trying to develop perception algorithms to increase the agility of robotic platforms, among which also drones, because they are among the most agile robots. And in order to do research, we decided to pick human drone racing pilots as a reference, because what they show with their acrobatics is that the problem is not the hardware. The hardware is perfect. It can be flown at impressive speeds and much better than machines. So what this shows is that the real problem for research is actually software. And so we started a collaboration with Marvin in order to understand what are the tricks that human pilots take advantage of in order to drive drones at these incredible speeds and agilities for performing inspection tasks, not just racing, by the way, because these FPV, first-person view drone racing pilots, are actually now applying their skills into other sectors like inspection. And this is amazing. And we learned a lot of things from this collaboration with Marvin.
Okay. Well, I'm sure that Marvin was excited to be able to contribute to drone research. Okay, so we'll move on to a couple of other points. So you posed the question of, can we outrace the best human pilots? And you said that the AI drone did win, but only with onboard sensing and computing. Could you just expand on that?
Indeed. So we organized a challenge where we invited the world champion pilots. We let them practice for many days, and then we let them compete against our autonomous drone that was using an onboard camera and an onboard computer. And we showed that thanks to the help of machine learning and neural networks, the drone could actually defeat them in controlled conditions. This was the first fair human versus AI race in the physical world. Fair because basically both humans and the AI were using the exact same drone with the same aerodynamics, the same mass, the same camera, the same field of view. Everything was exactly the same. The only one difference was that the AI was relying on an onboard computer while the human relies on off-board computation, because the human puts a camera that streams the images to goggles and then the processing is done from their brain.
Okay, yes, I see that. Okay, yeah, you talked about optimal control, limiting the range of behaviours that can be expressed by the controller. So you use, I think, was it repetitive learning, or what was the expression?
We use the reinforcement learning,
Reinforcement learning, yes.
which is a paradigm of machine learning, which allows an artificial agent, an algorithm, to learn a behavior by making mistakes. So from trial and error. So we basically simulated a drone that learned to fly by crashing millions of times, and then rewarding those navigation policies or trajectories that would actually go in the direction of the finish line, and penalize those trajectories attempts that would actually either collide with the floor or the gates or go in a complete opposite direction.
Okay, so that's a perfect example of the idea of break things and learn from the process.
Indeed.
Okay. Okay, so you had a clip where I think the theme was to do with learning from nature and how sparrowhawks catch garden birds. What's the particular learning from that?
So sparrowhawks show that birds are much more agile than any other flying platforms that we have built so far, like quadcopters. And this is thanks to perception, in particular because now the brain sits directly on board the aircraft. The birds perceive the world through their eyes, which do not work like standard cameras. Standard cameras observe the environment at constant time intervals, usually every 30 milliseconds, so 30 times a second. But the bird's eye works like the human eye. We have a continuous stream of information from the eyes to the brain. That means that you can already start making decisions in sub-millisecond latencies rather than waiting for the next frame in 30 milliseconds. So it allows us to actually push much farther the agility of a platform.
Okay, good. Okay, so let's move on to at the end of your presentation. You talked about the advantage gained by a combination of cameras, different types of camera. Could you just expand on that, please?
So standard cameras are great, and they are the main sensor of use for all intelligent cars nowadays. So I'm thinking not of autonomous cars, I'm thinking of advanced driving assistance systems, ADAS. So any modern car now has a camera behind the mirror that monitors the scene and detects other vehicles, checks for the safety distance, and alerts the driver if the driver is falling asleep or getting tired. The problem is that these cameras work like any other camera by recording frames at constant time intervals, typically 30 hertz, which means 30 times a second. Then now, if you think of a typical speed of a car in a city environment, 50 kilometers per hour, that means that the car during the interval of 2 frames actually has traveled 1 meter. Now, one image is not enough for these intelligent cars to make a decision on whether to engage the safety braking or not. They usually use 3 frames. That means 100 milliseconds or 1/10 of a second. During those 100 milliseconds, the car will have traveled 3 meters, and many things can happen in 3 meters. A toddler can jump on the street, and it's too late for a human or for a standard camera to see it. But this is not the case for an event camera. Why? Because event cameras are cameras that can see in the blind time between 2 frames. And they do so by recording the motion at the pixel level. Whenever a single pixel detects motion, that pixel alerts the computer that there is something that it should look at.
Okay, so it's this combination of 2 types of camera, the event camera and the standard RGB camera that is the secret to the success there.
That is correct.
Okay, good. Okay, so Davide Scaramuzza, thank you very much.